Hello everyone, my name is Human Zarinkub. I'm the Principal Product Manager for wireless products at MathWorks. And just a little background about myself. This is the 22nd year that I'm here at MathWorks, serving as Development Manager as well as Product Manager. Prior to that, I was in Nortel Networks for wireless communication company in Canada. And I got my bachelor's at McGill University in Montreal and my master PhD in National Institute of Scientific Research in the University of Quebec. I am joined today by my friend Ramiz.
Hi folks, my name is Ramiz. I'm an application engineer here at MathWorks, and I deal mainly with all of our wireless standards-based products. So anything to do with 5G, LTE, WLAN, and the system level simulation topics that we're going to address today. I come from a wireless background for many years as well. I did my bachelor's back in India, and then a master's and PhD from the Northeastern University in wireless communications. So let's get started, Human.
Welcome to this wireless network modeling with MATLAB live cast. If you want to take a look at what we have here for you, the agenda is as follows. Following some introduction and networking basics, we're going to essentially present into 4 sections. The Wi-Fi or wireless LAN networks, Bluetooth networks, the notion of coexistence between multiple networks, Bluetooth and wireless LAN in this case, and finally 5G networks. And finally, we're going to come back and summarize what we have learned. In terms of introduction, MathWorks, we have been involved with all types of wireless communication and their standards. So the goal of wireless communication is wireless connectivity, connect to internet, no matter what mode of communication you can have. You can have satellite communication, we call it global area network. You can have cellular communication, wide area network, local area network for your homes and offices, local area network like wireless LAN, or personal area network, your Bluetooth and so on. So MathWorks has invested in all of these modalities of wireless communication. And essentially, we started with physical layer and link level simulation, 2 radios talking to each other. And now we want to go and expand what MathWorks has for another domain of wireless communication.
The term ubiquitous connectivity comes to mind. It's been thrown around all the time, which is exactly what this is.
That's
right?
it. Ubiquitous means no matter where you are.
You want to be connected to something.
Yeah. And hopefully, when 6G comes in the middle of desert, you can have satellite communication and so on. So what are the typical, so we have been investing in wireless communication, especially physical layer link level. The next challenge would be to go for wireless network modeling, meaning not only the link between 2 radios, imagine bunch of wireless radios and they're talking to each other and how the network is analyzed. So what we bring as MathWorks is the ability to model, simulate, visualize, and analyze those wireless networks, and essentially in 4 different challenges that our customers are telling us about. So one of them is essentially see and feel and analyze the wireless networking components, like the nodes going through multiple stacks, traffic models, mobility. That's one of the elements that we are trying to learn from our customers and provide solution. And another one is the spatial aspect. No wireless network is in isolation. You have network topology, meaning how the network elements are arranged in space. And between each network element are channels. It could be wireless channels, could be buildings, obstructions, and all the scenario and channel modeling involved with that. That's a big part of network modeling. And then you can always notice that when you have wireless network modeling, you can abstract out what happens at the low-level physical layer, or you can include the exact data and the packetization and capturing and transmission and all of that together. And the measurements of how much did we go have a throughput, how much did we have bit error rate, packet error rate, and so on. So that's one of the things that is important for wireless network designers, to log and visualize and analyze what happened in a network. And of course, AI is a future, and it's coming to every possible area of engineering. and you want to be able to train and co-simulate with AI for the future so that all these different kind of management of networks can be trained.
Right. As a matter of fact, we talked about this, which is the 5G and the 6G standard. The 3GPP standard is including AI in their standards itself.
Even 5G Advanced, which is release 18, seems
right.
to have some AI. So it's not in a distant future.
It's not really, it's almost here.
Near future. All right. So let me just continue a little bit of networking basics and hand off to my friend Ramiz for more in-depth discussion. So wireless networks is essentially nodes and channels, right? A physical network node is a device that attached to a network, collection of these nodes, and capable of creating, transmitting, receiving information between the nodes using a channel, right? So the network is a group of these nodes which has a wireless medium or channel that is connecting them. And network topology is essentially the arrangement of these things in space. The distances, the geometrical arrangement is all about topology. So here I'm showing you an example of different types of network topology. From the left-hand side, you see star network. Cellular communication is notoriously in a star configuration. The base station is the king and schedules the transmission from base station to devices, from devices back, and that radiates out from a source. That's called star network. And if you look at the middle of your screen, you notice that we have this classical cellular infrastructure with those honeycomb kind of sectorized cells and handoff between the cells as the red dot moves between one cell to the other cell, right? So the client or our cell phones are moving around in that structure. Mesh network is another one that's very important, where you can have connection of every node with almost every other node as they request, or many of them. So there is no one directional. You can connect to, and that's the distributed network structure that is good for low distances like Wi-Fi and Bluetooth. So all of that is good and well, but we have, as of release 2023A, as of the March of this year, we decided to provide you with a library that enables you in MATLAB to model, simulate, analyze, and test this wireless network. It's called Communication Toolbox Wireless Network Simulation Library. You can either go to MATLAB in your desktop or online and go to Add-on Explorer and just put the word wireless network and find it. It ships with Communication Toolbox. So you must have Communication Toolbox before you can have it, or you can access to it directly using the link that my friend put in there for me. So now let's talk about things more in depth. Why don't you take it over, Ramiz, and tell us more about that.
So the first thing I want to do is actually walk you through a nice getting started example. But before we even get there, I want to show you a little bit about what's inside a node, what's inside a MATLAB node. And so typically inside a MATLAB node, just like you have it in a physical device, you have many different layers. For example, application layers that generate the traffic, MAC layers that do scheduling and figuring out who has access. Then you've got the physical transmitter and receiver. So this is where you've got your physical layer, you've got your transmit antennas, receiver antennas, etc. And then these are connected to through a common medium. In this case, it's a wireless channel. And depending on what standard you're using, be it like a 5G standard or a WLAN standard, these channels could be significantly different. And MATLAB has a whole bunch of these channel models that can be used to do this. Now, how do we do the simulation in MATLAB? We actually take a discrete event simulator idea, and we've extended it in MATLAB. It's all MATLAB based, which means that you don't have to learn any new tools. Everything that you've learned so far applies here. And we've just taken the same ideologies, and we've added a couple of different things. One is one of the nice features that we've added is this ability to perform actions during the simulation. So this could be things like add a node during the simulation, remove some nodes, see what impact it has on other situations. So without further ado, let's go switch into MATLAB and take a look at an example. And so in doing so,
you want to show the add-on first, how to access
yeah, absolutely. So let's figure out how to get the add-on first. It's a like we pointed out, it's a free add-on with the communication toolbox, and the way to get to it is using the add-ons tab right here. If you click on this, go and get add-ons. Let's just search for network modeling. And there's the library. And now, since I've already installed it, it says manage here, but if you haven't, it just has an install button. Takes a couple of minutes to install, very quick, nothing else needed, and you can install this add-on library. Now, once you
so it's a free add-on if you have communication toolbox. Just click on manage or install, and all those functions that you're going to show now appears in your MATLAB.
Yeah, no other task needed. Yep,
right,
just shows up. So let's go ahead and get started. And the way to get to this examples, the easiest way is to remember this nice command that I like, doc WLAN. It takes you to the documentation page for WLAN toolbox. And the examples tab is right here, so it takes you to the examples. And we are going to search for system level simulation. So these are the examples that model the networks. And so the example that I want to walk you through a little bit today is the getting started example. So it's right here. So we're going to go ahead and open up this live script. All right. All right. So let's take a look at it. And once we've taken a look at a little bit of the code, and we'll start running it so that we can analyze some of the results. So what's inside this? It's a very simple network that we're going to establish here. It's going to have just one AP, one station. This is just an ease of getting started. By all means, you can have many APs and many stations added to your network. So these are the stages that we're going to go through. We're going to configure the nodes, associate those nodes, configure some traffic that are going to go on these nodes, configure the channel model that we're going to use, and then run the simulation. So it starts out by deciding, how long we want the simulation. In the interest of time, I'm going to reduce the duration of the simulation. And then it starts out by also defining some abstraction methodology. Now, why do you need abstraction? Like Fuman was saying earlier, if you wanted to do a full 5-layer of simulation, it's great. It basically generates the IQ samples at the transmitter, passes it through the channel, receives it on the other end, and demodulates and decodes. But oftentimes, you can actually get a statistical model for that after you've done your analysis and use that model in your system level simulation. So that's what's happening here. So you can set those flags to whatever abstraction methodology you want to use. Same thing goes with defining the nodes. We have the WLAN device configuration object that defines the configuration set for this access points. And then we just add it into an access point and station node. So here's your WLAN node. This is a feature from the support package. Again, very powerful. You can just add it as a node to your network. Once we've done that, we just create those nodes and associate those stations. We just tell them, which station is associated with which AP. The next point is adding the channel, and once we've added the channel, we can go ahead and run the simulation and get some results out of it. So let's go ahead and do that, and let's get this nice timeline for the simulation. So we can see that it has one AP and one station, and we can see the simulation now running, and it provides you an airtime analysis of each packet that's going on. We can go ahead and zoom into this and take a look at what's happening in certain intervals, and look at that. You can actually see individual components of that MAC layer. So you can see what contention happened, RTS, CTS transfers. In addition to that, you can also see the idle times. And then you can also see packets being transmitted. So packet was transmitted from here, received on the other at the station. And
so when you transmit, that's green. When you receive, it's blue.
Yeah.
But then there is a collision. That's the yellow one, contention, right?
Yeah, so contention is, at the beginning where we try and say, I want this medium, I want to use it for the next.
Then there is a little bit of idle. If anybody's,
so that's the entire MAC in operation.
So all that MAC modeling is included here. Yeah.
Yeah. And in addition to that, you can also get metrics at each of these nodes. So if you, let's say, you want to know what was the throughput at the station or at the AP, you can calculate that. So it looks like we had a very simple setup. So it's obvious that we don't have any packet loss ratios, and not a lot of latency going on. But you can measure average latency and packets at each of these locations.
So that over there, it says you can do throughput in megabit per second, right? The next
yeah,
and multiple metrics, right? Throughput, latency, packet loss ratio, all of that is included in that one simulation.
Yeah, and even better is that there's a stats file that gets spit out afterwards, and it has a whole bunch of information in addition to the stuff that I showed you. So how many packets were transmitted, how many bits were transmitted, bytes were transmitted, what was the, if you had like some kind of aggregation of these packets, how much was that?
Yes.
All of that information is included.
So you learn by doing the simple one.
And you start by doing this, and then
you add node and make it more complicated.
So that's basically the idea.
You mentioned something, Ramiz, that I want to ask you. So you said that you download that add-on, right? But we have like 3 standard-based products that if you download the add-on, there is specific nodes and so on installed in them, right?
Yes.
So the way to get access to them is go to corresponding standard like WLAN toolbox, like 5G and Bluetooth, and there's a system-level simulation.
Yeah. So like I pointed out to you in the help example, just like I went here, every toolbox there has a system-level simulation documentation page, and from there you go to the relevant examples, and it showcases all the relevant examples. Exactly. So for example, every example in the WLAN toolbox is listed here. So we did the getting started example, but there are better ones out there, which for example, this is a residential scenario where you have multiple rooms.
Go through that.
And plus you have a whole bunch of other examples.
That's great. That wasn't that hard.
That was easy. All right. So let's go ahead and continue with our slides. And so we saw how easy it can be to set up and run a simulation with just a few lines of code. And here's another example of that. It's literally whatever we saw right now, even though it was spread out and there was a lot of explanation. Ideally, it was just 10 lines of code. It was, you can set up that entire simulator with just that much. Create an AP.
But that first command is key, right? Wireless network simulator.
Yeah,
all starts with that.
Yeah, that's your event-driven simulator. Everything from there on is just configuring it, adding the nodes. So it could be as simple as 10 line of code to get that going. All right. So now that we saw that, let me tell you a quick intro to the WLAN toolbox, just to make sure that we're all on board. The WLAN toolbox again is it's a wireless standards-based toolbox. It addresses the 802.11 standard, both at the PHY and the MAC layer. So at the PHY layer, if you wanted like that granularity, you want to analyze that physical layer, you can do it for all sorts of flavors of WLAN, going from 802.11 to all the way to the most recent, BE. I don't know if you've looked at it, Homan. There's this beautiful 4096 QAM.
AX, BE, even A, B, GN.
Yep.
All the flavors of 802.11 are included, and it's very good, becoming more complicated.
I always am amazed at that 4096 QAM 320 megahertz bandwidth signal.
In a very good channel.
Only in a very good channel, of course. So we saw a couple of different things in that WLAN node. So let's start at the top. A couple of different things that set up, it did not showcase in that example, was that you've got different application layer traffic models. So you can have just an on-off traffic model. You can have some video and voice calls, or you can have different types of traffic models again. And for those, you can configure the packet sizes, traffic rates. And you can, again, enable full buffer traffic, which means that your buffer is always, full with traffic for you to transmit.
Before you move on from this, so you can model on-off video, voice, and FTP traffic patterns.
Yeah.
So it doesn't mean you have to have voice and video actually
No.
but the pattern matches the video pattern, the way voice travels through voice over IP and stuff. So as long as you have bits and packets that behave like that, you can model.
Absolutely. And then I was talking about earlier, you've got the abstractions for the PHY layer as well. So you've got options to do full PHY, which means you're generating those IQ samples passing it through the channel that you've selected, and then running a receivers, checking CRCs to make sure that it's
full fidelity.
Full fidelity.
But takes longer.
It takes much, much longer. Whereas on the other side of the spectrum, you've got, usually people do it as, analyze that, take a statistical model from that, and then when you want to go run a system level simulation, take that model, give me a packet error rate table, flip a coin, and decide if, packet goes through or not for a certain packet error rates. All right. So in terms of topologies, we've got different topologies possible with the WLAN network. So you've got a simple one, which is infrastructure BSS. But in addition to that, of late we've seen a lot more of these mesh networks. So this is basically, I think it got introduced with like 802.11ax, Wi-Fi 6. I think most houses now have that, where you throw a couple of different meshes around in large houses.
Tell them all about that. Yes.
And then we've also got hybrid meshes, and this is why is it hybrid? It's because it's actually using different channels in the mesh. So like you can see, the mesh 2 and 3 are connected over the channel 61 and 6 gigahertz, whereas the AP 1 and 2 are connected over 21. So you can have this hybrid models as well. And the support package and the WLAN toolbox will actually let you evaluate these mesh technologies. You can also have your own custom routing algorithms and define, configure the paths in that mesh network. And like I was also saying, you can also have these much more complicated, multi-band mesh network. So
let me take over that one. So this is what I have, many of my friends and I have this kind of in our house, right? You're connected to internet through either a fiber optic provider or your telecom provider, and you have that wireless router, right? And the wireless router or AP access point, if you buy these mesh network version, you put multiple of them in different parts of the house, right? One upstairs, downstairs, in the living room. And these are essentially the routers that serve the stations. Stations could be your laptop, your iPad, whatever, right? And as you said, if you have a kind of multi-band mesh network, the access point or the routers can speak to each other, right, on a different frequency with bigger pipe they need. Whereas the connection of the nearest mesh AP or router to the station, could be a different frequency and different bandwidth. All of that is very easy to set up in this wireless network modeling, right?
Yeah.
Just some parameters and you have a wireless.
That's true.
Multi-band wireless mesh network.
Absolutely.
Good. Moving on to the examples, let me just emphasize what you said. So there are 3 products right now in MATLAB that are enabled. The network modeling and system level simulation of them is enabled by this wireless network modeling library. One of them is WLAN toolbox or Wi-Fi toolbox. You saw the examples that Ramiz showed. And you can go as small and start with the WLAN, get started, all the way to OFDMA, which means that you separate the frequency band for each connection, right, at the same time, but different frequency bands. Or you can have multiple other choices. Is there a multi-user MIMO in there?
There are a couple of examples that do multi-user MIMO.
Multi-user MIMO is right, because you have multi-users and they share same time and frequency, but because of the beamforming, they don't interfere with each other.
Yep.
That's great. So let's move on from this to the next topic. Bluetooth is another standard-based product we have. It's another standard that has a lot of networking in it. And from day one, we have included all the application and MAC and physical layer stuff into the Bluetooth toolbox, right? So you can do a lot of Bluetooth networking with our tools. If you go to,
I guess Bluetooth is unique in the sense that the SIG itself also defines a lot of the application and the
It's true. Let's talk about that. Most standards stop at MAC, right?
That's right.
They do a little physical layer, they do a LAC layer, they stop, and it's up to you to do all the other stuff. I guess SIG, which is
Bluetooth SIG is a little bit different.
It's a little bit more and does more specification. So for us to implement the standard base is easier. We just refer to the SIG documentation.
It's not left as an exercise to the user.
Exactly. But that's great. So topologies of Bluetooth, especially low energy, right, LE, are as follows. Bluetooth mesh is very important. You saw, almost every Bluetooth node talks to almost anybody as you like. But remember, we're talking about when it comes to Bluetooth, we are in personal area networks. Distances are low, the energy profile is low. So these are essentially, you want to pass the data through short links until it reaches the end user. But of course, the Bluetooth Piconet, there is a central, almost a base station called laptop or central guy, right? That directs the ACL links that you see between different things. So both of these topologies exist in Bluetooth.
Right.
And if you go to next slide, my friend. By the way, I would like to remind you that if you have questions, and we'd love for you to have questions, we will answer all of them at the end. My friend here is collecting them and making sure that they are queued up for us. Please ask your questions in the
the comment chat section,
and we will get
we'll
to it.
Absolutely get to it and answer it towards the
very soon. So notice again, Bluetooth Toolbox. We go to the system level simulation of the example. You see all these examples. You see how wonderful the actual stacks. In the second example, we have Bluetooth mesh flooding in wireless sensor networks from physical layer, link layer, all that stuff is included. Profiling the energy of Bluetooth mesh, right? Even the estimating the packet delivery of LE broadcast audio, how much delivery according to specification. There is a lot of examples that does network modeling in our Bluetooth standard-based toolbox, and we would like you to get to that.
Right.
Now I'm going to hand it off to you back, my friend. Talk about the other topic, which is a very important topic.
So this is an exciting topic, which is, we've heard a lot about Bluetooth and WLAN networks of late, but oftentimes they do exist in the same environment, and sometimes they do share the same channels. So how do they coexist? And you want to do some analysis on that and figure out what strategies you can use for coexistence. And in our heads, we've kind of formed these two big categories. One is non-collaborative coexistence, and the other one is collaborative. And as the name suggests, non-collaborative is where you could be on the same device, but really the transmitter and for like a Bluetooth and a WLAN network don't really know each other. So they're doing their own thing. Whereas on a collaborative one, they're actually mostly co-located, and you can have some kind of algorithms running to figure out who can transmit at what time. Basically they just play fair with each other.
Yes, more sophisticated.
So we've got a bunch of different things analyzing these networks. So the first thing we can talk about is coexistence and from just a interference perspective. So this is an example that we have in the toolbox, which simulates a Bluetooth LE or even the classic networks. It can use adaptive frequency hopping. So Bluetooth is capable of doing adaptive frequency hopping, and it can hop off and go off and then into different channels, and either categorize them as good or bad channels, and then hop off and be in a good channel. The advantage in this example is if you wanted to do your own channel classification algorithms, how do you classify them into good and bad channels? We've got plugins in there to do that. And again, you want to be able to measure performance, so you've got your metrics.
So let me ask you a question. So you have a Bluetooth network, right?
Mm-hmm.
And all of a sudden, the Wi-Fi in the same frequency turned on. Mm-hmm. And the AFH, the frequency hopping, learns how to avoid that band and choose other channels.
Yep, absolutely.
And that's all happening in one example. We know how it works. And a lot of customers have been asking us about that, right?
Yeah, this is a popular topic that we've been addressing off late. Given the popularity of Bluetooth off late, a couple of years ago, Bluetooth was probably used for just an image transfer from one phone to the other. But now we've got all these AirPods and smartwatches and whatnot. And I think even like data rates and Bluetooth have gone up. From like one image now to like completely streaming audios and streaming images and whatnot.
And that's why we have all these standard-based products, because we know that if you have one standard like Wi-Fi interfering with 5G, or Wi-Fi with Bluetooth, or Bluetooth with 5, if they have the similar frequencies, we have to have all of them.
Right.
All right. What else do you have, my friend?
So, so here's a classic example of that in action. So, like I was saying, this is a nice classification. So you've got your all of your different Bluetooth channels right here, and you can see that there are two WLAN interferences here. And once you run the simulation long enough, the frequency hopping algorithm kind of figures out that all of these channels need to be categorized as bad channels. You've also got some, you've got some advertising channels in between, but these are the other channels are the ones that are good, and then you can be used. And again, these are possible with you can have your own choice of classification algorithms also selected.
Do you think AI is going to play a role in the future on this? Learn,
this could
train?
be. I mean, it sounds like an AI problem to have. Sure. Yeah.
Right.
And AI is also looking at like for the wireless area, there's this whole suite of problems that we can address.
Yes.
But I'm yet to see like a nice commercial product come out of it. So it'll be exciting when that comes out.
Yeah. All right. What else do we have here?
So a couple of things that we wanted to explore is, so this is a classic example of a non-collaborative coexistence. And in this case, we're modeling both adjacent channel and co-channel interference. So you've got interference in the same channel, or it could be the adjacent channels. And you can get metrics like this, where you can get packet loss ratios in the presence of varying the power of the WLAN system. So what happens with packet loss ratios for each of those central and peripheral nodes when the WLAN is more powerful. So between Bluetooth and WLAN, Bluetooth has significantly higher powers. So in what impact does that have on the these metrics like packet loss ratios, throughputs, and average packet latency? So let's go ahead and take a look at.
Before you go, so you're on the same simulation.
Yep.
In the same timeline, and depending as a power as the main function, you have packet loss ratio, throughput, and average packet latency.
That's right.
Right?
Yeah.
And of course, you see the pattern. I mean, the more loss you have, the lower throughput, right?
Right.
And this is the throughput of what? The Wi-Fi or the Bluetooth?
So each of those lines point to a certain links right there, so you can see the legend. But what is important to note is that packet loss ratios go up when the WLAN power goes up. But that's not the case for the WLAN nodes, right? Because they perform better when that happens.
Nice.
All right, so let's take a look at this in action. So what I'm going to run is a collaborative coexistence example. Nice. So in this case, I'm going to show you what happens when you have some kind of collaboration in this. In this case, we are going to use what is called as the packet traffic arbitration, PTA. So it basically has a set of rules that defines what happens when either you have a packet to transmit or you have a received packet, who processes it and whatnot. So let's go ahead and take a look at that example in MATLAB. So again, coming back to our documentation page, the example that we want to look at today is right here, collaborative coexistence. So let's open up this live script. And let's walk through a little bit, and then we'll run it. I want to reduce this duration so that we can run it in a decent amount of time. But before we even get there, let's talk about what's the mechanism, right? So here's a nice picture that showcases that in the absence of a traffic arbitration, your packets are just going in and out of those transmit-receive chains. Whereas when you have that coexistence algorithm running, when you have PTA, the PTA kind of decides what happens with each of these devices. And we've explained a little bit about what they do here. So we've kind of put that together right here and tell you about what the PTA is doing. So if a node wants to transmit multiple packets simultaneously, PTA kind of decides which packets go through where.
That's the algorithm.
That's the algorithm, yes. But let's take a look at the actual setup. So you've got one smartphone, and you've got multiple links. One is a Wi-Fi link with the Wi-Fi router, and then you've got like most of us have this these days. It's headphones and a fitness watch So all of them coexisting on that smartphone. So let's go ahead and see how to set up that smartphone and then each of those other networks. Now, if you remember from our previous simulations, exactly the same thing. We've got your initial command just to get it going. I'm going to reduce this in the interest of time so that we can run it. After that, we're going to start setting up that coax node. Again, we use the same kind of objects that we used before. So we set up that device configuration as a station. We add that device to that coexistence node. Once we've done that, we go ahead and define the two other links. So you've got your basic rate, enhanced data rate, and then the Bluetooth low energy as well. So once we've set up that device, we now have to set up the peripherals. So you've got your Wi-Fi router being set up right here. The peripheral node for the Bluetooth EDR node, and then the LE node. So all of those are set up here. The WLAN nodes get associated, and then the Bluetooth nodes get configure that connection. The next thing is, like we said, add the traffic. So you've got some network traffic on off. Deciding here, we decide some kind of data rates, packet sizes for those. Once we've done that, we have to define the traffic for basically for all of the
so
each of the
traffic
links.
On off.
So in this case, we've traffic. You've just
one kind of traffic.
One kind of traffic. It could be anything else.
Add it to your traffic source.
Yeah, exactly. And in this case, now we are going to use the PTA. So we you can enable or disable that. Once we've done that, add all of the nodes to the simulation, and just run the simulation like we did before.
Just
pretty straightforward.
That object, right?
Yep. And we've started following this coding paradigm in most of our tools, which is you want to add you have an entity, you want to add it to another entity. So it's just it's literally call that entity with the first input being the object that you want to add it to. Yeah, it's true for a lot of our tools.
So there's an object, and we add properties to it, right?
Yes. Yeah.
And then that object, we just say run it, and it runs the simulation.
And one of the bigger advantages that I see in doing something like that is that when you don't want to configure a lot of things, you want just the basic thing going. You don't have to write a lot of code. You just defaults.
Yes.
So use the defaults. So here's that nice
what are we
simulation in running. This is exactly the same transition state transitions that we saw earlier, but in this case now not just one node, not the two nodes. We've got a bunch of these different links. So we've got that going. But what's interesting also is that you can see the traffic in the WLAN traffic right here, and all of the Bluetooth LE and the Bluetooth the classic Bluetooth traffic also in these little plots right here. So you can see that some of them are in the same spectrum. And like I said earlier, the more you zoom in, you can get a lot of additional information as well. So like that WLAN traffic, you can see, that's the WLAN traffic. And once you zoom out, you can also see the relevant Bluetooth traffic in the adjacent channels. Again, Bluetooth is using some kind of frequency hopping techniques, so it also keeps hopping off and on.
But this system runs a Wi-Fi link and two Bluetooth links, and
yes.
all of that is modeled in one environment.
Yep.
And all the contention, all that stuff is handled, and then we have the wonderful display of all the results.
And I hope you can see the powerful nature of this tool, which is that at this point, the WLAN is not just an interferer. It's not a signal that's interfering. It's an actual node that is transmitting data and packets, just like it would do in an actual environment. So, yeah. And you can decide the traffic rates for this. Like for example, if you wanted, let's say, the Wi-Fi router to be doing, the Wi-Fi link to have like a call going on, like a video call going on, and then see what impact it has on a Bluetooth, audio transmission. You can do such things very easily right here, because now each of them is a full node.
Let me ask you one thing.
Yeah.
So we have a bunch of off-the-shelf, on-off video, audio traffic models. I think we can, our audience can write their own traffic models too and add it somewhere, right?
Absolutely. So going back to that, one of the main important features for most of these tools, WLAN, 5G, LTE, the Bluetooth, is that we've opened up all of this code as white boxed code, which means that you're able to kind of open and look at this code and edit it to your
and
heart's
change
content.
it right there.
You can change it right there. So
if you have a
exactly
different traffic model, different algorithms for the contention handling, all of that.
Code. Yeah.
So everything is open. Good job. All right, let's go back to see. I want to make sure we get to the whole presentation on time. That's great.
All right, so the last item that we want to talk about is 5G networks. And 5G networks is a it's a little bit of a more advanced topic, and 5G with its much more complicated physical layer, and we in a lot of these cases we want to be exploring scheduling methodologies. We've got a whole bunch of things, and as of 23A, we actually introduced the 5G node features as well. So you've got your the G node Bs and the UEs as just like another node in the wireless modeling package.
Before we show the demo, Ramiz, could you go back to the last slide? I want anybody to know, on the left-hand side, we see all these different characteristics that are mostly phi related, right?
Yep.
So we support FDD and TDD,
yes,
right?
That's true.
In the 5G toolbox. We support all numerologies, right?
Yeah.
You can abstract the phi, or you can go through the phi. The compromise between speed and accuracy. And of course, uplink and downlink and all of those reference signals and all kinds of stuff. And we have also in the product different kind of scheduling, where the base station
around best CQI. Or,
best CQI, this and that, round robin scheduling. So these come with a toolbox itself, right?
Yes.
And then with opening up this wireless network generator stuff, we add new stuff to it.
That's true.
Yes. That's great.
All right, so in this case, we're going to take a look at the wireless network simulator for a 5G network. And one of the popular things that MATLAB has enabled a lot of our customers to do is build apps. And a lot of our customers just use the app designer, the MATLAB app designer, to generate a lot of these apps. So I went and created one.
You wrote the app?
We wrote an app too for doing some wireless modeling. So let's go ahead and take a look at that app and see what we can do with it.
So if you're as good with MATLAB as my friend Ramiz, you can do this app.
Yeah, and it's yeah. So let's go ahead and run that. It's going to take a couple of seconds to come up.
I think we should give this app in the link of this call later on in GitHub or something. They can maybe
sure, and if you're interested, we'll talk to us, and we'll work with you in getting some of the stuff. Like Human was saying earlier, also, if you have questions about any of this stuff, feel free to post them, and we have somebody monitoring it. We're going to be answering all of those questions in a little bit. We've always had this thing about asking good questions. You know what the good questions are, Human? The good questions are the ones where we know the answer for.
How do they know what the answer for? Ask any questions you want. We get there. If you don't know, we don't know.
So in this case, we're going to add. Let's create a new session. We're just going to have one cell. We're going to create one G node B and a couple of nodes. Let's go ahead and create that node. And you can parameterize this to your heart's content. You can parameterize the G node B. You can have scheduler configuration. So like I was saying, you could have round robin, proportionally fair, or best CQI. You can do the MCS selections for the uplink, the downlink. You can enable multi-user MIMO if you have to. In the interest of time, again, I'm going to reduce this.
So our wireless network simulation has the G node B type of node and UE type of node. So what you did, you called that and configured this.
Yeah, it's just
by
a
calling the existing function.
Yep.
What you see here is just the MATLAB, front end to that.
So it's just an easy way to do all of that.
Visualize it.
And we've also got a whole bunch of visualization tools right here that you can look at. So let's go ahead and simulate this nice scenario, and you can see the throughput plot as a function of time. And so like I was just simulating for a very short duration. You can see that come up. You can also visualize the CQI grid or the resource block grid for the simulation that we are working with, you just have to mark which one we're going to analyze. So let's go ahead and analyze that.
So you look at the channel quality indicator grid. What is the channel quality when you run this?
And this will also show you, which resource blocks were allocated, which slots used which UEs. In addition to that, you can also, look at the performance of these things from a
aggregate
from a cell perspective, and instead of looking at it from just a single user or single perspective.
And you can do all of that with the underlying basic functions. You just make it nice and neat so you can do that.
Here's something else. So you can actually export that and generate a MATLAB script for that. And once you do that, we generate a couple of different scripts. And here's that necessary script that exactly the same as what we were seeing earlier. Here's your network simulator initialization, creating the G node B, creating the UEs, and off you go and run the simulator and collect some KPIs. So you can generate that script
graphically first, and then you generate the MATLAB code that you can go and explore it and find out exactly what's happening underneath the hood. That's great.
All right, so let's switch back.
I think it's time for us to kind of finish our slides and get back to
go and answer some questions. All right, like I was saying, we've got a whole bunch of different examples here. Different channel models to explore as it goes with 5G Toolbox. If you've not used it, let us know. Amazing tool. It's got the all of these different channel models that are required, TDL, CDL channel models, and all of those can also be used with the network level simulators. All right, so Huma, you want to do some conclusions?
Let's do. So again, we are introducing wireless network modeling capability to our existing wireless standard-based toolboxes. The three of them that we show today are 5G toolbox, wireless LAN toolbox, and Bluetooth toolbox. You saw how we start with the wireless LAN Wi-Fi network, APs and stations, and there are a bunch of examples. What we call examples is like a design patterns. You can go, and if this kind of problem you're solving, you'll see it almost completely done, and we can add more to it. On Bluetooth, we do that, as well as 5G. And another application that all of customers are talking to us about is the coexistence and interference. These networks don't run in isolation, and they do interference and coexistence. And we show you how algorithms can be introduced to handle the coexistence and interference issues. And as my friend Ramiz said, because everything is a MATLAB source code, you can go in there, change anything you don't like. Traffic pattern, the algorithms for scheduling, the algorithms for contention handling, and so on and so forth. With that, is there anything else that we have here?
Just a couple of pages for product pages that you can go and refer to and get to. One of the good things that we've started doing at MATLAB, and we've been doing it for a couple of years, maybe decades, is everything examples-wise that you saw today, they are also part of the documentation that we publish online.
Yes.
So if there's an example that you saw today, you just want to walk through it a little bit or learn a little bit more. We're going to post those links down in the description, and also some of the comments are going to have the links.
So you don't need the MATLAB code at all to see what's going on. You can go online and look at every of these examples and see our nice documentation and all the list of MATLAB code to achieve that. If you want to actually run it and design it and change it, you get the evaluation copy of these toolboxes and with the free downloadable add-on, and you will be in business.
Absolutely. All right, and with that, I'll leave this nice page up so that you have, which support package to download. But I guess it's time that we got to our questions.
We are open for any question that you may have. Thank you so much. That's the first question. Let's read it together. What are the advantages of using MATLAB over other tools? Let me take that.
Yeah.
MATLAB is not a language, my friend, anymore. It's a platform. So under MATLAB, you have vertical products and vertical solutions. And usually, a problem like wireless networking has antenna ramifications, has RF ramifications, have digital ramifications. Because MATLAB platform and the products, you can combine this into designing almost the full end-to-end solution. A solution that enables you to do the link level simulation, system level simulation with all those different speciality and algorithms that you need for each domain. This is the main advantage. And because we open everything up in terms of MATLAB code, it's an open environment for you to explore and get the maximum for your application. These are the two reasons that I can say.
If I may add, Human, one more thing is that a lot of our standards-based tools are, perfect implementations, or nice implementation of the standard itself, right?
Yeah.
So we actually give the advantage. You don't have to go and read the standards and in order to do that work, and it could be significant work where you have to, read the standards, implement it. So we kind of let you focus on the task at hand instead of, we provide the tools so that your application can be
that's the main advantage of using a standard-based toolbox like 5G, WLAN, satellite communication, Bluetooth. We have read the standard and implemented MATLAB code for it. All right, is there any other question that we can see here? Let me see. Why don't you take a look at that? Go ahead.
So could you take, sorry, the question is, can we talk about using these models when developing DSP applications such as firmware in HDL coder for 5G?
Nice.
I think the short answer is that we've got a whole great bunch of tools that can enable you to go from your algorithm to your implementation in a single platform. So we've got the wireless HDL products and the DSP HDL products that will enable that workflow. It's it's a great workflow. We've automated some of that process, made the implementation and we've also got this whole model-based design that helps you, model all of your physical entities first, and then you can go from there into your implementation with some automatic code generation steps.
Yeah. Let me just add a little bit.
Yeah.
So algorithm is the king for us, right? So these contention and different traffic models and all that stuff is open MATLAB code. Right now, to go to implementation on the hardware, use them as reference, right? And you do your low-level stuff and you compare. Gradually, as time goes on, we will create blocks in Simulink or system object that generate that HDL for you automatically. We have done it for 5G and wireless LAN and toolbox physical layer stuff, and maybe in the future, if you need it, and depending on your need, we might add that capability.
Tell us.
Even that is a push button. You don't have to write your own thing. But the path from algorithm to implementation with HDL coder and Simulink wireless HDL toolbox exists.
Yeah. Tell us and we'll make it.
Yeah, it's true. Well, if we can.
If we can.
Is there anything you see on the thing? Let me read that for you and see what you can do. As far as I know, Starlink satellite communication communicate with each other. That's it. Satellite communication is definitely a wireless network. Can this toolbox be used to model such communication, accounting for position, single attention? Excellent, excellent question. Yes, this is the beginning. This is the beginning of general networking, which includes satellite communication networking. What we showed you is the examples we put in those 3 products as a version 1. The version 1 came out in 23A. It's only 6 months into it. But yeah, we are thinking about extending it to our fourth standard-based product, which is satellite communication toolbox, which has the ability to also model that. And absolutely right, the Starlink or any other commercial satellite constellation, there is a Kuiper by Amazon and other people, they have actually a networking capability, meaning that the satellites talk to each other using either RF or optical
links.
Optical links. And of course, satellites talks to the ground station using mostly RF links. But yeah, this technique can be used for that. And also, because our satellite communication toolbox comes with beautiful visualization, geocentric visualization of satellites and airplanes and drones and cars on the ground, you can actually do the simulation with that scenario, get those distances which are updated as a function of time, and using those distances and so on, create link profile and combine. So it's not a fully done by us yet, but we are going there, hopefully, with your help.
But addressing this specific question, though, Human, which is the Starlink satellites, a lot of these satellite constellations actually have what they call as TLE files, two-line element files that are updated, on public websites. You can just download those TLE files and have them read into Satellite Communication Toolbox and populate an entire bunch of satellites, have them visualized, and you can account for, things like exactly the stuff that you're asking about, position, signal attenuation. You can also, account for things like propagation losses. So let's say that you don't want to just account for free space path loss. You also want, losses due to rain, fog, cloud, atmospheric scintillations. Those are all, possible with the satellite communication toolbox.
That's great. So, which toolbox would you suggest to analyze spectrum congestion? So, spectrum congestion is included in this library which ships with communication toolbox, right?
That's right. TSP, so I want to kind of clarify, this may be coming in from like two different angles. One is analyzing the spectrum itself, which is exactly what we were talking about, which is, a DSP spectrum analyzer will let you analyze, any piece of spectrum. And again, you can also have hardware connectivity with it, so which means that you can have like a couple of $100 worth of radios on the table.
SDRs.
Yeah, software-defined radios can capture signals off the air and analyze a specific spectrum and see what's going on there. In terms of talking about spectrum congestion itself, that's a little bit of different topic, but we kind of address that with like the coexistence scenarios where we have either like co-channel interference or adjacent channel interference. And so that'll be one way to analyze it. And one of the nice features in the toolbox is that you can, as we go through this process, you can record IQ samples at each of those nodes, which means that if you wanted to look at specific spectrum details in those at each of those nodes, you can do that.
I think I'm going to ask my friend here who asked the question to contact us directly through our 5G or wireless LAN product. There's an email button to me, and it seems to be a multi-product solution. They want it, I can see it.
Right. It could span a couple of different
areas. So send us an email, and we will get smart people involved and get to your answer better. Do you have any upcoming webinars that go more in depth on each of these toolboxes? Yes.
Oh, excellent question.
So if you mean toolboxes on the networking side, we may have new, fresh, more elaborate version of this coming up as a webinar, MathWorks webinar. But if you're going for the corresponding toolboxes like 5G and so on, yes, we are planning. We are lucky that almost every month we have a wireless communication webinar, public webinar available. And all you have to do is go to mathworks.com and look for events, and you see the timing of those webinars. But definitely we go in depth through each toolboxes, which contains physical layer as well as networking functionality in them. That's a very good question.
Yeah, we are pretty active with the community here. So if you just go to mathworks.com, go into the events and look at upcoming events. Like Huma, you were saying, not just the public webinars, we also have some,
we have localized
topic level webinars. We have like
seminar. Next where you are, I was in different parts of the US for that, and we are very active also in conferences. So I'm going to go to next conference, GlobeCom, and you can see me at the booth there. All right. So what else do we have here? Any question that my friends have for us? That could be it.
That looks like it.
Well, feel free. We are here, and we are happy to answer any questions you have. Hopefully, you got to see that we have introducing a new functionality in MATLAB that was essentially we wanted to do that for a long time. We started with standard-based products like 5G, wireless LAN, and so on, physical layer. Now we are adding networking layer. That is a good question. Why don't you go ahead and see if you can.
So the question is, how does the Doppler shift affect the communication link between a Starlink satellite and a ground terminal? Can I simulate this using MATLAB?
Absolutely.
Absolutely. The question, so the specific, this is actually a shipping example right now in the satellite communications toolbox. So if you were to just maybe even Google satellite communications, Doppler and latency with the words MATLAB in it, you'll probably see that to be the first example that shows up. Again, for a Starlink satellite, like I said, if you just go and download a TLE file from websites like Cellestrack or Spacetrack, you can download the TLE files, and once you've downloaded that, you can just import it into MATLAB and have a satellite populated. As a matter of fact, we do have some webinars that are coming up in the satellite area. If you wanted to attend them, we're going to cover some of these topics there.
The latest setup, my friend Mike McLernan has that. So please go to mathworks.com/video, look for satellite communication. The latest one has this. And you know, in satellite communication, because LEO satellites are very close to Earth, 500 to 1,000 kilometers above the Earth, they are not geostationary and they go very fast. The plus and minus Doppler shift is about plus minus 80 kilohertz, I heard. So major challenge of equalization is taking care of compensating for Doppler shift. And these examples that my friend is talking about, Rami is talking about, does pre-compensation as well as post-compensation, meaning that if you know the speed of your satellite based on TLE, you pre-compensate that.
That's right.
And if you don't know, or you do it and it's not perfect, you find the residual amount of Doppler shift, and there is an algorithm we put in there, and you can change it if you want, to completely compensate for a Doppler shift. That is a main challenge, and without that, the satellite communication will always be suboptimal. But that is something that we have put a lot of work into it.
All right.
Yeah.
It's a great question. Thank you.
That was an excellent question. Yes. So our examples that are ready to play with hardware, that is the domain of what we call a wireless HDL toolbox. It's a product in MathWorks that essentially takes our 5G, Wi-Fi, Bluetooth, satellite communication, the most expensive algorithms like the channel modeling and the modulation and OFDM and so on, and creates Simulink models that are essentially equivalent to the MATLAB algorithm, and generate using HDL code for that. For example, for 5G, the first thing you have to do with 5G is turn on your cell phone and connect to the network, which means that you have to read the MIB and SIB information. We have it all play with hardware as of many years now. So yeah, just open,
And since this was a pretty open-ended question, this said hardware, I want to add to the fact that everything that you said, and then I also add the fact that we can also interact with a lot of software-defined radios. So you know, if you have like USRPs or analog devices, Pluto radios, MATLAB will actually interact directly with them. You can build transmitters, receivers, everything with it. And we also have if you wanted to go like look at for instance like 5G or WLAN, the really wide band signals. So we've got the wireless test bench that will actually enable that workflow. So
this is the testing part, meaning that there is an app we have called Wireless Waveform Generator app. You change set the frequency, the bandwidth, all the parameters, and it generates the waveform, and then one click of button, it goes to either SDR or RF
wherever
instrument.
you want it to go.
So if you want to play in a sense of generating and transmitting over the air, that's also something we have as a click button, as an app ready for you in 5G and wireless LAN and Bluetooth and satellite communication toolbox.
All right.
Right.
Next question.
Yeah, go ahead.
The question is, I'm doing research on optical wireless communications. Can this be experimentally analyzed using MATLAB?
We are starting with that, right? We are starting with some of in our product, especially satellite communication, some optical communication channel models that we read from the standard bodies or contributions from different universities. It can be done in MATLAB, but if you want to go deeper, please contact us through the links in the invite of this presentation, or on 5G Toolbox. There is a button to contact me at the bottom. We are getting active into gathering more MATLAB functionality for optical wireless communication. Right,
and it also comes down to what medium we are thinking. Not medium. What network we are thinking about here. If it is like a satellite network or a lot of the in-home networks are also starting to think about Wi-Fi. Optical from the light bulbs and
that's
whatnot.
Why he's doing research.
We'll be interested in hearing more about it and probably have some resources that we can point you to.
It's an active area of interest for us at MathWorks. So we would love to hear from you if you want to give us more on that. That's great. Well, more questions.
Oh, I'm loving this. Can I use MATLAB to track the latency and throughput of a Starlink connection over time? The short answer is yes. But when you say throughput, you have to understand what the underlying standard that is being used. And off the top of my head, I don't know what Starlink uses.
We have DVB-S2 support. Right. We have DVB-S2X. We have DVB-RCS if it's DVB, if it's digital video broadcasting. Some satellite uses LTE or 5G.
5G, exactly.
We have that.
Say we have got support for 5G as
well. But we need to add the link level simulation stuff, at least the modulation and coding and stuff to do the throughput, right? Or you don't need that?
You can calculate throughput even now because you've got there is a, in the 5G toolbox, we've got for a 5G example, an NTN, we've got a throughput example that calculates, PDSCH throughput.
It's a table lookup, right? Based on some kind of
No, we've got an NTN example that actually implements an entire end-to-end link with the 5G. So we've got a 5G channel model in there as well.
So the answer is, if it's NTN, if it's non-terrestrial network version of 5G, we have an example for this.
That's right. Yeah.
So yeah, talk to us about that. I'm going to show you, if you want, if you send us an email, we'll show you the link to that example. Just go to 5G Toolbox and look for, or satellite communication.
So go to Satellite Communications Toolbox and look for an NR PDSCH NTN throughput example.
NTN is the
NTN being the keyword there, because if you don't do NTN, you'll probably end up with the 5G example.
We have done it, but we need to go deeper on that. So that's great.
And once we're done with this, I'll probably pin a comment that has the NTN link.
Nice, nice. Any other question? What time do you have, my friend?
We are going a little bit over right now.
So that's it. Thank you very much for attending this wonderful live cast. And again, my name is Human Zarenkoop.
And I'm Ramiz. It was nice joining you today. And
find us on mathworks.com and send us email and connect with us through the link on the YouTube. Thanks a lot.
Absolutely. Thank you.